I'll be very happy to present to you the Tabular Q Learning technique. We're going to start by reflecting on some of the content we covered in week 1 and 2, just to get a few reminder or refresh our memory of what we've done, and we're going to build on top of that, define a problem set that's a little bit more complicated than all the things we've encountered so far. And to solve that problem, we start by getting an intuition of how Tabular Q actually works. To get that intuition, we're going to simplify our complex problem and also look at simplify the solution as well and do a walkthrough just so you can see how it actually works when it does work. And then we'll formalize the actual Q learning algorithm and do an exercise. I think it would be nice to spend an hour tonight to do that exercise with our support on the floor, and then we'll get back on the screen, look at a scenario where we're dealing with continuous state spaces and see how we can tackle that. I'll walk through the takeaway homework so you get a view of what the solution might look like, but then you have to go away and actually experiment yourself to actually solve that. And then we'll just do a quick key takeaways for this week, and get a view of what you might expect next week. During today's talk, if you have any questions, please raise your hand, because we don't want people to be lost throughout the entire duration. And also feel free to come up to any of the tutors during the break or the exercise period or even afterwards to cover any concepts you don't understand this week or last week or the first week. Does that sound okay? All right. So week 1, Paul introduced you to the reinforcement learning problem set, where you typically have 2 entities. The first one being the agent and the environment. The agent is the AI that you're trying to build, and the environment is the world that it tries to interact with. Typically, the agent will receive from the environment an observation or a state, you call it. An observational state can be an image from a camera, or it can be sensor readings, temperature, how far the robot's arms are angled, things like that. And given this information, the agent would have to make a decision on what it wants to do next. It needs to take an action. And by taking an action, it interacts with the environment, which moves a time step forward, and the environment will provide a next feedback in terms of state. But by taking an action and moving into a new state, an observation, the environment will also provide a reward. And in reinforcement learning, the reward is one of the key concepts where the reward will inform the agent on whether what it just did recently is a good action or not, and help it figure out what is the best action to do given any scenario. In week 2, Artem talked about the Markov decision process, and it provides a formal framework for viewing the world and the environment. I've blatantly stole an image from Wikipedia, just so we can quickly go through some of the concepts covered, just for refresher purposes. So the Markov decision process includes a tuple of state, actions, probability of an action, the reward of taking an action, and the concept of discount. What we have here in the diagram, we've got 3 green dots to represent the states that are available in our MDP. We also have actions that are available to the states in the form of orange circles. Now you'll see these numbers attached to these orange circles. These are probabilities of transition, in a sense that if we're in state 0, we want to take action 0, there's a 50% chance that we're going to end up back in the same place, or 50% chance we transition to state 2. You also notice some wiggly lines here. These indicate the reward the agent would get, or the actor would get as it transitions. For example, if you if you're in here, take this action, you transition over there, you get a reward of 5. Alternatively, if you take this action, you're unlucky, there's a 30% chance that you have a -1 reward. As part of week 2, you also learnt about dynamic programming, about solving this problem set by breaking it down and repeating the solution over and over. The alternative is, we can just take a look at it and go, hey, it's pretty obvious. We want to somehow end up in here, take this action, hopefully we'll get lucky and go over there and repeat. Now, what we see here is in reinforcement learning, you can call it a perfect model of the environment. We understand exactly how everything works, exactly what happens, and the probabilities as we step through this process. In reinforcement learning, you call this a model of the environment. And a model embodies all the dynamics of the world, and with a model, you know exactly what's going to happen. Now, in reality though, as we build AI for the real world, there's going to be scenarios where you can't have a perfect model. For example, friction is one of the most challenging things you can potentially model. If you have a robot, you want to move forward by a meter, the floor could be slippery, or it could be windy, and potentially your sensor readings could be wrong as well. Nothing is 100% in the real world, or we are unable to model that 100% yet. If we think of another scenario, think about a robot trying to interact with a human. The robot might take an action. How do you model what a human is going to do? Because everybody could react completely differently. So when we think about it from this perspective and looking at what we've learned so far, it might be easy to go, what's the whole point of this, right? Yep.
Not all the transitions and states have rewards.
That's right, and that's possible. Yes, yes. You can have 0 rewards. So in this scenario, all of the transitions, there's only 2 that actually provide non-zero rewards. Any more questions? Yeah, no? So, yeah, the question is, you want to ask is it still all useful, right? The answer is, yeah, the multi-arm battle problem, and he's like, I got this down pat. I'm going to take this to the casino and make them bankrupt them. So he heads off to the casino with his pen and paper, because he needs his pen and paper to build his Q table. He's going to hit the slot machines and find the best one. And as you do when you go to the casino, you probably start off with a few drinks, because that's what you do. And so Paul starts off by heading to the bar. All right, he has a few drinks. Unfortunately, he hasn't had enough sleep, so actually after 2 drinks, he actually passed out. So he actually wakes up somewhere in the casino, right next to slot machine 1. And to his surprise, it's not just machines, laid out in front of him. The casino is actually organized in grids, and each grid has 1 slot machine that might provide a specific reward. And he doesn't know which machine will provide what reward. And from an action perspective, he now, if we take a top-down view, he now actually has to navigate around the casino. So his actions become moving up, moving down, moving left, moving right to navigate this. And also, he doesn't have a map of the casino because he's a little bit intoxicated and he can't visualize too far, right? He's also intoxicated in the sense that when he wants to move right, he might end up staying still. That's what happens, right? Or if he moves up from here to there, he might end up going that way. So, and when he explores this casino, he's gonna sometimes stumble up into here where this slot machine 6, it will give him a -1 reward. And he's going to get depressed. Oh my God. This is where he goes, I'm going to have another drink. And he passes out. Thereby ending an episode where he will wake up somewhere else on the floor somehow. And if he goes into state 10, well, it gives him a +1 reward. And he's like, yeah, I'm going to come here all the time. I'm going to stay here, has a drink, passes out, wakes up somewhere else again. There's another episode. So what we have here is an episodic scenario with random transitions, in a sense that, you know, he moves up, but he doesn't quite always end up going up. And also there's the concept of delayed rewards, right? Because as he moves around, he receives nothing until eventually he gets lucky and hits one of those. Does that scenario make sense to everyone as a setup? Yeah? Okay, so Paul's intoxicated, but he's not that bad, right? He's lost his long-term memory, but he actually has still a short-term memory. So he sort of remembers what he did in the last couple of seconds. He also has his pen and paper, and he can sort of roughly scribble onto his paper. And so in this scenario, he's like, oh, I vaguely remember some tabular Q technique I learned somewhere. Maybe I'll try that. So let's see how the tabular Q works and how it might work out for Paul. But before we dive in, I want to talk about just tabular Q in general and get a sort of high-level theory on it, I say. So the tabular Q technique is about learning the Q function, or you can view it as learning the Q value. And Q value is about, given a state, I have a value for the actions, for the action associated with that state. So for example, if I'm here, I have the option of going left. If I do take the action left, I want to know how good it is to take that action. And it's about assigning a value to an action given a specific state. And so if we think about where I'm here, you know, I could go forward, sideways, backwards. So each of those actions could have a value assigned to that to help me evaluate how good it is to take a specific action. Now, Q values are inherently estimates, unless you have a perfect view of the model, and then you can actually get the exact value. So that's the objective of Q learning, figure out what our Q values are, given the different states and action pairs. Tabular Q is also a form of temporal difference learning, and the word temporal means time related, and more specifically it's temporal difference zero, or TD0 learning. And that is essentially saying it's a method of learning or approach to learning where you don't wait for a long time before you start doing your learning. For example, if I'm starting in the city, I'm looking to go to Parramatta per se. When I'm in the city, my knowledge of how long it might take to get to Parramatta might be 50 minutes. But I decided to go west, and I'm in Broadway. And now that I'm in Broadway, I know that based on my historical experience, going west again to go to Parramatta is actually 25 minutes. So what I'm going to do is use what I know of Broadway and start updating the action value of going west from the city. Without actually taking the entire trip, I'm updating my estimate as soon as I've taken the next time step. So it's using an immediate experience and what we know of that experience, and actually updating what the action was actually just taken. If we look back to last week, in terms of the Bellman optimality equation for Q, you will notice some similarity there, in a sense that the optimum value of Q given a state in action, assuming we are in this state and taken that action, the value for that state action pair is the expected return plus a discount of this funky formula thing. What this is saying is, given a state, the next state, and the actions available in the next state, I want the value that maximizes this. So what it's saying is, pretty much, yeah, I'm updating, my value is with assumption that if I take a step and I continue to take actions that maximizes my value every time step going forward. And you will see how familiar this is with the actual Q learning algorithm. So let's look at the Q learning. This is the full algorithm. It's a little bit complicated and dense to start off. So let's narrow it down to one update. And still, that looks a little bit complicated, right? And to illustrate how it works, I'm going to simplify it a little bit more. Let's set alpha to be 1. By nature of alpha being 1, we actually negate all of the Q function calls on the right side, which leaves us with, does this look familiar? So now our Q learning algorithm becomes, hey, I'm just interested in the reward and what I know of the next step. Let's see how it actually works when we play it out, right? So let's also simplify the scenario I described earlier and assume Paul's actually not that intoxicated. When he actually does go up, he actually does go up. When he wants to go up, he will go up. So let's bring certainty into it so we can illustrate what actually happens. So Paul's going to start off and explore. Epsilon 100%. First thing, he tries to go left, and he applies his, can anyone see this? Or is it too low? Sorry about that. But it's essentially the Q algorithm where, you know, Paul, he goes, I think that's right, yeah, he goes right, and he receives a reward of 0, and he looks at what he knows of state 0, because he ended up in state 0. He goes, I don't know anything about this, and so my max Q of SA for this state is also 0. So by applying the update algorithm, he assigns a 0 value to the state of S1 and taking a left action. Goes up, pretty much the same thing because he moved from state 0 to S4, 0 plus max of all zeros, 0. And as he travels a little bit further, he gets lucky and it's eventually ended up in S10. What happened there? Sorry, passed out. Yes, passed out. Definitely passed out. But what's interesting is he takes a right from S9, ends up in S10. He gets a reward of 1 this time. By the fact of getting a reward of 1, he applies the algorithm. The reward is 1. And also, one thing to remember about terminal states is that there are no actions associated with this. You cannot take any action, so there are no values. There are no action values associated with terminal states, or they are, well, you set them to 0, basically. So by applying the update algorithm, he's got a 1 here. So he's slowly building up his table of Q values, and that's his knowledge of the casino so far. He wakes up, he passes out, wakes up here again, just for illustration purposes. He goes, I'm going to go to the other side. I'm sure there are better, poker machines around. ends up in S6. Following the same approach, updates his Q values. This is a table, or the table values are there to make it easy to read. There's a -1 here. Another episode, he walks up that way and ends up in S10. And you notice as he travels from S5 into S9, what's happening here? He receives a reward of 0, because by entering this state, the reward is 0. But this new state that he enters actually has Q values that are non-zero. So by applying this formula with a discount of 0.9, he updates his Q value for S5 and going up to be 0.9. Make sense?
The discount factor, how do you decide if the discount is or that?
So the question is, how do you decide the discount factor? It is definitely up to you. Mathematically, the discount factor that you use has an impact on how far it propagates back. If you're interested in values that are far into the future, you want a value as close to 1 as possible. But if you're not interested in values in the future, then yeah, your discount can be 0 if you're only interested in the next state.
If you're a large maze, you probably want a high discount value.
Yeah, so the comment here was, if you're in a large maze, you probably want a higher discount. And I absolutely agree with that. Any more questions? Yeah? Sorry, can you come up? I can't hear you properly.
Just wondering, for the path, do you go from there in the middle, or why you can't go to the left cycle and then to another round and then go to the step?
Does that help?
Yeah, sort of like a loop first. Like why you choose that path?
So you want this? Well, I've just chosen a few selected paths for illustration purposes. You can consider it, he got lucky, right? I'll show you what it looks like once he's done all of the random encounters.
This is just a randomly you picked up.
Yes, yes. Or more for, I picked these paths to illustrate to you what happens when you hit a negative and what happens when you hit a positive. And we'll get to that. So if he decides to go down this way again, you see the number 1 actually propagating back over there. 5th attempt, you see another value propagating back as he got lucky again. This time is 0.81 because the discount of 0.9 is 0.81.
So why don't you update S5 and S9?
Yes, you are definitely updating S5 and S9, but by applying this simple formula, the reward is 0. The maximum value in S9 is 1. You apply a discount, still 0.9.
Do you have a scenario where after multiple journeys from the S9 to S10, that number, like, it always be 1?
In this simplified, the question was, do we have any scenario where as we update S9 to S10, the value of taking a right action will actually change? And in this simplified scenario, it doesn't change because the reward is constant. You're always going to get a reward of 1 as you go into that grid.
For S9, what happens if we randomly just go to S8? Would that also rewards for S9 to be slightly lower?
So the question is, if you go from S9 into S8, what happens to this value? Is that right?
Yeah, to S9.
So the value of going left from S9, if we apply this formula, the reward is 0. The maximum Q value in this state is 0.9. And you apply gamma on that, 0.81. One more question? Is that your question? Well, the question was a bit early. So once Paul's done sufficient exploration, and by just randomly stumbling around and actually taking notes, this is what he will ultimately end up with. Does anyone know why that's 0.9?
You end up back in the same state.
Yes, that's right. In here, he's going to try and go up, hits a wall, it's like, oh crap, in the same state, but there's a time step. So by applying the formula, the maximum value is 1, therefore you have 0.9. Given now that he's built he's fairly confident he's explored enough, he can switch to greedy mode in a sense that every time he passes out, regardless of which state he wakes up at, as long as he knows what state he is in, if he wakes up in state 4, he only needs to, by being greedy, he only needs to look at the action values and go, hey, I'm going to pick the action with the highest value. And continuing to follow that, he will always end up in S10. Make sense? So with this simple illustration, I hope you have an appreciation for how Q learning can through sheer brute force experience, if you call it, you can actually arrive at a fairly optimal solution, and you can actually see the rewards propagating back once you visit each state action pair sufficiently.
So switching from the exploration to exploitation, are there any parameters here can be counted to say when do I do the transition?
From my experience, so the question was in switching from exploration to exploitation, how do I decide how to gradually shift that? I think, from my experience, there's a bit of art and trial and error actually, but you can certainly do that as you measure how much you're changing if you wanted to. I certainly haven't tried that yet, and you get to play around with that in the exercise.
I'm thinking actually if you apply probabilistic formula to calculate this number, there may be a confidence level attached to it. And if this confidence level, obviously earlier will be very low, but when it goes beyond certain thresholds, maybe that's the time to switch.
So the comment there was, as we explore and update our Q value, we can potentially get a measure of our confidence level as we're updating it, and as that confidence level goes higher, we can start gradually reducing exploration. That is something I've not played with, but potentially someone has explored it, and yeah.
One thing, so if it can be a simulation of a RL problem, you just run many simulations for each setting, so you can get a cost for each strategy.
So let me try and repeat that, and let me know if it's not correct. So the comment or question was, so in RL, if you run many simulations, and with certain settings, you can sort of figure out which one is the best. Is that correct?
Yes, but is that? No, that's correct. I just wondering, is that how you would figure out what's a good strategy, by calculating the cost?
Yeah, there's a bit of that, and you can actually apply reinforcement learning on a reinforcement learning framework to figure out what is the best parameters, right? If you look at Google's AutoML, it's essentially using a reinforcement learning framework to build a neural network that achieves the best results for a specific task. Yep.
What's the difference of this Q learning from value evaluation using a random policy? It seems the same to me.
Value evaluation using a random policy. Are you referring to last week's material? Yeah. So last week, you could say that. It's very similar. Just last week, you tend to have your transition probabilities known. And in this scenario, you don't. And that's where you see the difference in the next couple of slides. This simple one is the same. The simplified scenario is definitely the same as last week in that you're simply updating the next state by just trying random walks. Any more questions? Okay, let's get back to our Q learning algorithm. If we step back and go, hey, now we want to look at this stochastic or random transition scenario again, our simple formula is going to have a problem. Because our simple formula is saying, I'm going to update my Q value with the reward from my next state, and also assign the maximum action value from the next state. And this has a huge assumption in that we always end up in the same state. But when you're in a sort of random scenario, you could end up in multiple states with multiple rewards and multiple action values. So this kind of assumes that whatever we just experienced is the truth, and in reality it's not. And so if we think about that as in, the left side of the equation is our current knowledge of the Q value, and the right-hand side is the knowledge we gathered by simply taking an action and experiencing what happened. Then if you think about the difference between what we know and what we just experienced, in reinforcement learning that's called the TD error, so time step or temporal difference error. In a sense, it's a difference between what we know and what we just experienced. So to cater for random scenarios, instead of taking our experience in 100%, we are going to increment what we know with a small portion of that difference or that error. Does that make sense?
Why are you taking?
Okay, so the question was why.
Yeah.
So how do we know the value of an action when 50% of the time it ends up in a ditch, 50% of the time it ends up in a really good spot? And mathematically, that's to take an expectation, right? Averaging. In some ways, this enables averaging, because by being in a state, taking this action, you're going to randomly experience the probability of being in that state or the other state. And so we're, over many iterations or many attempts, we end up with the expectation or an average of what the value or what the action actually is worth. Yep.
How does the alpha affect the error?
So the question was, how does alpha affect the error? If you're familiar with deep learning, right? The idea is to slowly come to a solution. In a similar way, the alpha is just saying I want to take a small percentage of what we experienced into my knowledge, rather than taking that 100%.
So it's not hyperparameter.
In Q learning, it's not really called hyperparameter, but you can think of it that way. Yeah.
Is it fixed, like it's a fixed number, or it's changing?
So the question was, is alpha fixed? I think to do it nicely, you probably want to be finding a way of slowly reducing alpha as you become more certain. But in our exercises, we're not going to bother with that. Yeah.
So is it a number less than 1?
Alpha, yes, alpha will be a number less than 1 because we want to only add to our knowledge a small percentage of what we experienced. Yes? Yep.
I might be misunderstanding this, but would the error be kind of like the difference between the action that we just experienced and stuff like that compared with a more theoretical calculation of what you already know?
The comment was, would the error be the difference between what you've experienced and also what you already know? Is that the right?
What you've experienced and what you calculate on what you should have experienced based on what you know.
Yes, yes, yes. Think of this is what you currently know, because that's the value you have installed, and that's what you just experienced. Yep.
If you are starting and you have like all zeros, and then you find out like the next action is actually 1, isn't that going to give you like a -1 because you are getting your actual expected minus the actual? Isn't like going negative?
Sorry, I'm not quite sure what you mean there.
Like if you are starting everything with zeros, and then now the actual value is 1. When you want to update the key value, now you are getting like you expected 0 because you initialize everything with 0, minus a 1 that you are learning. Isn't that giving you like a negative value of what you actually want to learn?
Oh, right. So the question was, if we start with everything 0, and we have an action value that's 1,
yeah.
Do we end up with a -1?
Yeah.
If we look at this error formula, this is what we experienced, so the 1 will probably appear here.
Oh, okay, I thought you were the other way around.
Yeah, so the 1 minus what you know, you end up incrementing it positively. Okay, let's look. Given now we sort of understand the Q update formula, let's move back to the actual algorithm, right? The algorithm suggests we start with an alpha that's somewhere between 0 and 1, and epsilon greater than 0. We initialize all of Q values for all states, all actions, arbitrarily. I don't quite agree with this because the agent shouldn't know anything about the environment, and it should explore and build its knowledge as it goes, but that's okay. And we look through every episode, we receive our initial state, and while the episode is still going, we take an action given a state using epsilon greedy in a reinforcement setup. By taking an action, you receive a reward and a next state S prime, and we just apply what we just saw in the previous slide, the Q update algorithm, and so on and so on and so on.
What would epsilon greedy?
Question was, what does epsilon greedy mean? From week 1, epsilon greedy is explore, exploit. If epsilon is at 1, we have 100% exploration, so we'll take random actions. If we're greedy, then epsilon is at 0. If epsilon is at 50%, then there's a 50% chance that we take a random action and 50% chance that we take the best action we know.
So it's sort of like a confidence level.
It's more like a rule to determine whether we just try something or do we just stick with what we know best.
So a question about using the greedy algorithm. Would you use it per action or per episode?
So the question was in regards to the greedy algorithm. Do we take it according per action or per episode? Certainly in implementations I've seen it's per action, because I can't quite answer why, but it actually makes sense to me, but I can't put my hand on it actually. Yeah. Because actually, so if we're in a scenario where we know mostly what our state action space is like, we're actually wasting time if we're just randomly exploring. We still want to generally head towards the best path, but still sometimes explore to the side a little bit to still have that spirit of exploration, while where most of the time we're going to head in the right direction. If we do exploration per episode, then some episodes are going to be wasteful. Especially in a scenario where you have massive state space, chances are the exploration is not going to get anywhere, if you know what I mean.
Okay. If the epsilon for this step we choose to explore, to exploit, so basically, but we will still update the Q, right?
So the question was, if epsilon, or if we land on a random action, or we are actually taking epsilon action, we still update Q, and the answer is yes.
But it seems to me, even it's exploit, and when we update, the Q will still move, will still change.
Yes.
So it sounds, even it's exploit, it's still learning. It's still.
Yes, regardless of whether you're taking greedy action or explorative action, you are still updating Q and you're still learning. The concept of epsilon is so you can explore state actions pairs that you may not have visited before. Because if you're always greedy, you're always going to take the best action, and therefore you're never going to visit any other action, and so you never learn.
Sorry, what do you mean by Q terminal?
Sorry, say it again?
What do you mean by Q terminal?
Oh, right. What this is saying is, for any terminal states, there are no action values really.
So terminal state means get reward 1.
Or in some scenarios, terminal state don't have any rewards. But it's just saying when you apply the Q, this is important to remember for your exercise. When you have a terminal state, this is 0. Because there are no actions associated with terminal states.
Just trying to help understand, if we select epsilon to be 1, basically, we started immediately greedy, what will be the Q we learn?
So the question was, if we start epsilon at 1, immediately,
what will be the Q we learn?
What will be the Q we learn? Epsilon has no relation to Q values, right? Because epsilon does not exist in this formula. So epsilon is just a way for us to explore any.
Yeah, basically, without any explore, we start a greedy immediately, what will be the...
Oh, if we start a greedy immediately, well, you're gonna... How do you pick 4 actions that are all 0? Because you don't know anything about your actions. You're greedy, you're like, I have 4 actions, they're all 0. I don't know, maybe I'll blow up.
It's initialized arbitrarily.
Well, by arbitrarily means, I guess you could do randomly. I suppose you could do randomly, yes. I'm actually, used to the concept of 0, but you certainly could do random. At that point, if greedy is 0, then you can also start learning. That's a very good point. Okay? Yeah, one more. In this scenario, alpha tends to stay still. Yeah.
Sorry, I'm not sure if I'm going ahead. Like, you're talking about off policy, and you're using the policy when you choose A from S. Isn't the off policy meaning that you are not using the policy in your algorithms?
Okay, so the question was, you're choosing off policy, and isn't off policy mean you're not choosing the the action that you acted on. So Q learning is off policy in a sense that you're in state S, you've taken action A, and you're taking the reward into your learning, but for the discounted value, you're actually not choosing the action that you acted upon for your next state, but you're choosing from the next state the best action. So in that sense, it's off policy because if you did a rollout or if you acted on multiple time steps, you may not have taken the highest value there because of you might be exploring, but you update using the highest value to your knowledge. Is that? Yep. Okay, I think we better start moving on to the exercise part, otherwise it will take too long. So we're going to do an exercise. The exercise is in OpenAI Gym, of course. I've just blatantly stole their code so we can add a very simple scenario of Gridworld where you've got a horizontal grid of 8. You get a reward of 1 if you go right, and you get a reward of 0 and you fall into a pit and episode ends. And you always start here. So as the first exercise, and then we can go through it, and then you can apply it to more complicated Gridworlds and see what happens. And hopefully you also get an appreciation of how the Q value updates. Okay, hold on a sec. All right. Hello? Looks like I have to hold it like it. Quickly, I thought I'll do a walkthrough. No? Sounds like not everyone is familiar with some of the syntax, so I thought I might quickly go through the solution so you can try, it might help you to implement it yourself. So to implement, getting our Q table is essentially just all relying on the work of a dictionary, right? So to implement getting the Q value given a state and an action, well, it's just going to be using our state as the key and taking from the value retrieved there, whichever action it is. Before I go into here, I just realized there was a number of questions asking about how do you insert the state, and it's quite important that we use a tuple, wrap the state around a tuple. That makes, I can't remember exactly why, but tuples work better as keys into dictionaries rather than straight numbers. I can't remember exactly why, but please do, because in reality it's not going to be just which grid you're on, because it's going to end up being this sensor reading and that sensor reading and some other sensor reading, right? So tuple is the right way to go from there. Max of Q, well, that's just numpy max on all your actions given a state. Assigning a Q, pretty simple. I've also just created a function to check that if my state don't exist, initialize it. And there's also a specific scenario where if you want to take the greedy action, if you've never seen that state before and don't have any value for the action, well, it's going to be all zeros. How do you take a greedy action of all zeros? You're going to have to do something there. In terms of the implementation for the agent, pretty straightforward. In the get action, you're going to go, well, take a random number. If this random number is greater than my epsilon value, then I'm not exploring, so I'll just take greedy action. Just give the state to your Q table and say, give me the best action given this state. Otherwise, just do a random action. In terms of training, also fairly straightforward. Just wrap your state around the tuple, and just call get action because you've already wrapped all the logic for your policy in here, depending on your epsilon greedy. Call environment.step, which gives you back your next state, your reward, and whether it's a terminal state or not. Definitely wrap your new state in the tuple so you can do some operations with it. And we want to go, hey, what's my current queue and what's my queue for the, what's the maximum queue of the next state, and pretty much apply that algorithm or the queue update formula with this code. And then loop through again. Hopefully that's pretty clear. If not, keep trying. I'll put up answers later in the week. Feel free to message me in the forum if you still don't get it. But because of time, I'm going to start moving on.